Right.
that all I can do is sleep, so.
Excellent. I'm glad I found your way out of your stress.
But you know, as long as you can do something concrete and it doesn't involve waiting for registration to open in the morning, works quite well.
So what other courses are you taking?
I'm taking genetics and French poetry and an Africana studies course on women empowerment.
Wow. So are you thinking about becoming a biological chemistry major?
Yeah, I'm gonna do probably biochem and French culture.
And you're pre-med?
Yeah.
How's registration looking?
Successful. What about you?
It was, I had it yesterday, but it was.
Oh boy, nobody's here.
Actually, I forgot about registration.
You forgot?
Yeah.
How was that?
Oh, it was fine. I got everything. Yeah, my roommate and I woke up around 9. We're like, oh.
I know a senior who didn't get into her classes.
Wait, really?
Yeah.
Wow.
That's rare.
Oh.
Usually,
That's sad.
yeah, but like probably if she emails the professors, they'll.
Oh yeah, obviously.
Okay.
That's why registration shouldn't be scary, but it is.
Yeah. Well, it's more scary for younger.
Yeah.
Yeah.
I remember last year.
Yeah.
Oh, this is my lunch. Okay.
Yeah, everybody wanted to get.
But that's okay. We'll do it. No, so I heard my teammates had heard.
Anybody wants lecture notes?
Let's just say age 15 years this morning.
Anybody else wants lecture
Did you get
notes?
into a couple
No?
classes?
Everybody got lecture notes?
What? I'm taking Oreo with him.
Oh, me too. I'm having a spot in another class because I've heard.
You know, I was talking to no, I wasn't talking. I was talking to Sophia who was talking about him again. And she said that he's not after that one. So.
I don't know. I like Carla though. She's nice.
Good.
Carla.
Let's go.
Yes.
Is she teaching 205?
Mm-hmm. But our class filled up like in 2 seconds.
Literally.
So it was a very sad day.
Who else is teaching 205?
Her.
Oh no.
Okay. Only those two?
Yeah. They don't have a lot of sections for 205.
Excuse me. Excuse me. Excuse me. Apparently I've lost my last lecture.
I don't know.
What is? Where did you put my lecture?
No, but like seriously, you go into that
Just
class.
That's I was like,
You know what? I didn't get it.
My Mondays and
class.
Thursdays are
Rachel, do you need lecture notes?
Dude, my schedule just in general is totally.
Shanda, do you need
I
lecture
have a
notes?
class that goes from,
You have it.
like I have classes that go from 11 straight, no lunch, through 4:30 on both Tuesdays and Thursdays.
that happens to me this semester, so I'm so sorry. Because I have that Tuesday and I'm always like starting by the time I get out of lab. I'm always like, God.
My Mondays I start at 8:30.
Yeah.
I have a lunch, but then I don't end until 5. And Thursdays. It's Monday and Thursday.
I'm gonna be leaving on like the 7 a.m. bus to go into town to volunteer on Mondays. It's gonna be fun. Bring the women's hospital.
Okay, so the first 10 minutes I'm going to spend reviewing lecture 20.
Okay.
All right? So, the second law of thermodynamics states that the entropy of the universe must increase for a spontaneous process. And that's what is shown here. Entropy change for the universe, which is the sum of the entropy change of the system plus the surroundings, has to be greater than 0 for a spontaneous process, or it is equal to 0 for an equilibrium reversible process. So this is a reversible process, this is an irreversible process. So we see that we need to incorporate the system and the surroundings to determine whether a process is spontaneous if we use this formulation of the second law of thermodynamics. But it turns out that because most chemical reactions are conducted under constant temperature and constant pressure conditions, we can define a new state function such that we pay attention only to that state function for only the system, and we can determine whether the process is spontaneous or not. And that state function is the Gibbs free energy. And the definition of Gibbs free energy is G is equal to H minus Ts. Okay? Now let's look at the change in Gibbs free energy. Therefore, delta G is equal to delta H minus T delta S minus S delta T. Okay? The change in G is the change of H minus Ts. And that's equal to delta H minus T delta S minus S delta T. This should look familiar to those of you who've had calculus and you have used the product rule for differentiation. Okay? Now, I'm going to say that delta G is equal to delta H minus T delta S. What did I assume going from here to here? I couldn't hear that, Alice. Oh, it was Anna. Go ahead, Anna.
Temperature is constant.
Temperature is constant. T constant. So if T is constant, this term here goes to 0. Delta T goes to 0, and then we have this final equation which applies only to constant temperature processes. Okay? Does that make sense, Zoe? Okay. Yes?
You said a little while ago that most reactions, you say it's constant in temperature and pressure?
Right. Most reactions are conducted under constant temperature, constant pressure conditions.
Does this assume constant pressure?
No, this doesn't assume that. But if you have constant temperature and pressure, then the second law becomes delta G of the system is less than 0. This equation here, delta S universe is greater than 0, becomes delta G system less than 0 for an irreversible, spontaneous process. But this equation only works under constant temperature and pressure conditions. We proved that in class. This equation works under every condition. Questions? So, then the question is, if we want a spontaneous process, we want delta G of the system to be less than 0, but delta G of the system is actually delta H of the system minus T delta S of the system. So what combinations of delta H and delta S are possible? These are the different combinations that are possible, and corresponding to those combinations, you get different values for delta G. Extra copies of the outline are out there. So if delta H is less than 0 and delta S is positive, then this is negative, this is also negative. Therefore, for every temperature, delta G is going to be negative. So the reaction is going to be spontaneous at all temperatures. So I'm going to just change this and make this delta G reaction, because as chemists, that's what we are interested in. So what we really want to find out is what is delta G of the reaction. That's going to tell us whether that chemical reaction is spontaneous or not. To calculate delta G reaction, we have to first calculate the standard free energy change. This is the free energy change. This is the standard free energy change, and we denote that with a superscript O. This corresponds to reactants in their standard states going to products in their standard states. This corresponds to reactants at any state going to products at any state. This is what we're looking for, but the first thing that we have to calculate is this quantity here. So one way to calculate this quantity here, delta G naught reaction, is to say that delta G naught reaction is the Gibbs free energy of formation of the products minus the Gibbs free energy of formation of the reactants. These values are quite often tabulated. So looking at a table, you can calculate what is the change in the Gibbs free energy when reactants in their standard state are taken to products in their standard state. Or you can calculate delta G naught reaction by first calculating delta H naught reaction and then calculating delta S naught reaction. There are two different ways of calculating delta G naught reaction. Okay? So we now know how to calculate delta G naught reaction, but we still don't know how to calculate delta G reaction. That's what we really want. So how do we get delta G reaction? To obtain that, relationship between delta G reaction and delta G naught reaction, we have to understand how the molar Gibbs free energy of a substance changes with pressure. Why? Because delta G naught reaction assumes that reactants are at 1 bar and products are at 1 bar. Delta G reaction doesn't specify what the pressures are. So if we know how the Gibbs free energy depends on pressure, we can go from delta G naught reaction to delta G reaction. Yes, Anna?
What is the bar on top of the G mean?
That means molar quantity, okay, per mole. So this equation, which I derived in your notes as optional material, it is totally optional. I just want to show you that I'm not pulling a rabbit out of a hat. This equation allows us to find a relationship between delta G reaction and delta G naught reaction. And that relationship is this equation here. We derived this in class on Monday. Delta G reaction is equal to delta G naught reaction plus R, which is the gas constant, T, which is the temperature, the natural log, P sub C. We are looking at this reaction here, A plus B, simple A, going to C plus D. Okay? So what this is saying is that it's the partial pressure of the product raised to the stoichiometric coefficient multiplied by the partial pressure of the other product raised to its corresponding stoichiometric coefficient divided by the partial pressure of the reactants raised to the stoichiometric coefficient, and so on. Very important equation. You will of course be given this equation on an exam, but if you can remember it, it will help you in many courses later on in your studies in chemistry. So now we know how to calculate delta G naught reaction. We can use this method or this method. R is a universal constant, T is the temperature, we assume that you can measure that. And now what you need to know are the partial pressures of the reactants and products. If you know all of these quantities, then you know what delta G reaction is. And if you know what delta G reaction is, then you can determine whether the process is spontaneous or not. Yes, Rachel?
Should be given the partial pressures?
Yes, if you're, that's exactly what I did in the problem that was shown last, right here. Okay? So you're given delta G naught, and you're given the partial pressures of the reactants and products. So you're just using this equation to get the delta G reaction. So now let's look at something interesting. We said that for an irreversible spontaneous process, delta G reaction is less than 0. What will the situation be for a reversible equilibrium process? What will the condition here be? Delta G reaction is equal to 0. So at equilibrium, when the concentration of the reactants and products are not changing, this is the condition that has to be satisfied. There are notes out there if you don't have a copy. Outline. Okay? So that means that delta G reaction is going to be 0. If that is 0 at equilibrium, then delta G naught reaction is minus RT. This quantity here is what we call the reaction quotient. And the reaction quotient evaluated at equilibrium is called the equilibrium constant. This ratio here, which we call the reaction quotient, products over reactants. This quantity evaluated under equilibrium conditions is called the equilibrium constant. So normally this is Q, but Q at equilibrium is K. Therefore, delta G naught reaction becomes minus RT natural log of K. What is K? K is the partial pressure of C to the power C, partial pressure of D to the power D, over the partial pressure of A to the power A, partial pressure of B to the power B, all of these evaluated at equilibrium. The products over the reactants evaluated at equilibrium is the equilibrium constant. Very, very important. This quantity evaluated at any condition is called the reaction quotient, and that's given a symbol Q. Question, Taylor?
No.
No, okay. But that was a 20-minute summary of what we did in lecture last time. Okay, let's move on to okay, so you get to see another one of my favorite movies. So it demonstrates a very important characteristic of equilibrium, but on the other hand, it demonstrates incorrectly another very important characteristic of equilibrium. Can you tell me what are these two characteristics? What is correct and what is wrong about this movie?
It's correct that it's going back and forth.
Exactly, it is correct because equilibrium is dynamic. It's got a dynamic piece of music to go with it. So let me play this over again. What's wrong? Sorry, Anna?
I have no idea.
You have no idea. Okay. it is in complete contradiction to this concept here. What this equation is telling you is that if you look at the ratio of the products to reactants, that ratio is going to be a constant, K, equilibrium constant. But if you look at the ratio of the products to reactants in this movie, it's changing. Okay? To really fix this movie, they should have had lots of molecules of reactants and products and made sure that the ratio remained constant during the course of this movie. All right? So, these are two very important concepts related to the concept of equilibrium, and that's what we're going to talk about today. So remember, we derived this equation here, delta G naught reaction. Delta G naught reaction is the change in the Gibbs free energy when reactants in their standard state are taken to products in their standard state. That is equal to minus RT natural log of K. Where did this equation come from? This equation came from delta G reaction is equal to delta G naught reaction plus RT natural log of Q. Q is the reaction quotient. So at equilibrium, delta G reaction is 0. Okay, I want to remind you again, I have extra copies of the outline at the back. Delta G reaction is 0. That's this here. And Q becomes K. And that's how we get this equation over here. So this equation tells you the relationship between delta G naught reaction and equilibrium constant, which is this quantity here. So let's look at this equation here. R is a constant, T is a constant, okay, let's assume T is a constant. Okay? Delta G naught reaction is a constant. Whether the reaction is conducted at 100 atmospheres or at 1 atmosphere, delta G naught reaction is the same. By definition, it says it is the change in the Gibbs free energy when reactants at standard state conditions, which is 1 bar, are taken to products at standard state conditions at 1 bar. So whether you do the reaction at 1 bar, 10 bar, or 100 bar, delta G naught reaction is a fixed quantity. You can look that up in a table. So this quantity is fixed as long as the temperature is fixed. It's independent of pressure. So R is a constant, and if we assume T is a constant, what can we say about K? K is a constant. Okay, very, very important relationship. So K is independent of the pressure. It depends only on temperature. Let me repeat that. The equilibrium constant is independent of pressure and depends only on temperature. Okay, that's a lie, but when you come to Chem, I'll tell you it's a lie. But for now, we're going to pretend that it's true. we can take this equation, delta G naught, that equation there, and we can write that equation as K is equal to e to the power what? Who's talking? Who is saying something? I can't hear. Is that Tiffany?
Oh, I'm just thinking out loud.
Yeah, please go ahead.
Is it e to the negative RT?
Negative?
Other way around.
That can be written as e to the power minus delta H naught over RT times e to the power delta S naught over R. Okay, using simple algebra to rewrite this equation. Yes.
I don't understand what you mean by like delta G naught reaction is a constant. Like if it was a constant, it wouldn't like equal another equation, would it? Like
What I'm saying is that delta G naught reaction is independent of pressure.
okay.
Because it is independent of pressure, R is independent of pressure, T is independent of pressure, therefore K is independent of pressure. K depends only on temperature.
Okay.
So, delta G naught reaction is the Gibbs free energy change between the reactants, which are here on the left hand side, and pure products, which are over here. So here are the products, here are the reactants. So delta G naught reaction is this quantity here. Okay. At equilibrium, delta G reaction is equal to 0. So at equilibrium, this quantity is 0. And what you find is that this curve here has a 0 slope. Basically, what I'm saying is that if you plot the Gibbs free energy as a function of progress of reaction, the slope of this curve gives you the delta G reaction, the quantity on the left-hand side. The delta G naught reaction is the energy difference between the reactants and the products. Okay, I'm not proving this, but basically what you can see is that if delta G naught reaction is negative, then products are favored. Why? Because if delta G naught is negative, then this quantity here is going to be positive, and e to the any positive quantity is going to be such that K is greater than 1. What is e to the power 0? 1. So e to the power any positive quantity is going to be greater than 1. So if delta G naught is less than 0, then K is greater than 1. If delta G naught is greater than 0, K is going to be less than 1. And if delta G naught reaction is equal to 0, then K is going to be equal to 1. What would delta G naught reaction equal to 0 mean? That means that the reactants and the products have the same Gibbs free energy. That means that at equilibrium, neither the products nor the reactants are favored,